So we'll begin by going through the first course, or the first week, January 22nd, 27th. I don't think we need to review the course, this type stuff. We now know all this. Where was the first? We defined GIS. I probably would ask too many questions about these very first slides, but just to review. We talked about GIS being hardware and software to integrate mapping and attributes. As time goes on, you're seeing that more and more. I think the first half recorded without audio. I'm going to have to redo it. The default is without audio, and I didn't change it, so hopefully that works. But anyway, I fixed it for now. The GIS is a process-oriented definition computer-based system that provides for collection, storage, analysis, and display of spatial data. By now, maybe you can think of some examples of that you've seen either in class or working on the labs that satisfies that definition. GIS is also a decision support system, following the integration of different reference data. And I've mentioned, I think, where I work, we use GIS for decision support all the time. Company X wants to build building Y here. Should they or shouldn't they? Based on a variety of different environmental, cultural, structural, engineering criteria. So that, in essence, that's a decision support system, and GIS plays an important role in that type of environment. Most information has spatial component. 80% of all data is spatial. In other words, 80% of all data can be linked back to a point on the Earth. Your address, even the classroom, even when you get your scheduled classroom, Fillmore 355, that's a spatial data. Fillmore 355 has a location on Earth. And many of these things that might have been somewhat new to you the first week are hopefully more second nature now. The fact that we have these layers, and each layer is a different GIS data set. It might be of counties. Someone was working on the lab where you had, land use areas in Massachusetts and then roads in Massachusetts. So that's two layers. The roads in Boston is a layer. The polygons that show land use is another layer. This slide illustrates that basic point. I mentioned GIS use is widespread just about everywhere, and that's growing. I was looking at you folks' background, and it dawned on me there's been a dramatic change just in the past years. I think 6 of you, or maybe it was our geography majors, and that alone is a major change to me in the past 3 to 5 years. But earlier than that, it was all GIS was a geography discipline, and now a small minority of you are geography majors. I think that's fantastic. I think it's great to see. It just further illustrates this slide. Because of that, there's more opportunities for you when you graduate using it. I think that's a trend that I've just seen very recently that I think is very good for the industry and very good for you. GIS is more than just ArcMap, but it is hardware. Obviously, you're running them on a computer or other devices nowadays. So you need hardware, you need a computer or device to run it on, you need the software, you need data. Your labs wouldn't be very exciting if there wasn't data to use in the labs. And people and procedures, you need people trained to use it, that's why you're here. I gave some examples. I really wouldn't ask about these because these are examples from later in the course, and I'd probably ask about them later in the course. But just refresh your memory. We talked about drive times to businesses. We talked about mapping water mains and how to shut off if a water main's leaking using GIS to tell which valves you have to shut off to isolate that water main from any water. They're having a horrible time in the last month because this freezing weather just makes them so brittle. There's been so many water main breaks. My friends might have been out. It's bad enough when it's -5, but at least I'm at home. They're out digging through, trying to find a leak some of these nights lately when it's 5 below zero. So I feel bad for our water department friends. this is the worst possible weather, especially when the water main's under pavement. The pipes are brittle from the bitter temperatures and big trucks go. The vibrations from trucks can actually help the water main snap easier, so it's the ones near the road that are most susceptible, and there's been a lot. I think I saw in the news there was a big one on Broadway today even. I saw that somewhere if you were down that way. Or remote sensing, raster data. We talked a little bit about raster data. After the first test, we'll talk a lot more about raster data as we get into March. This is an example of locating specific habitat. In this example, this is Bolivia. They're looking for an endangered fox. The endangered fox prefers a certain habitat. So if you want to find the fox, you find the habitat. We did a similar project in New England looking for the Canadian lynx, which is mostly extirpated or gone from the lower 48, but not necessarily in areas in New Hampshire. There's still lynx left. So we employed a raster data model similar to this to look for the habitat where the lynx might be found, rather than just blindly trudging through the whole state of New Hampshire trying to find the lynx. We isolated our search areas to areas where the vegetation and land type matched where the lynx prefers. Okay, now we get that out of the way. I mentioned this just before the break. We talked just before the break about degrees, minutes, and seconds. Or that, and if we look at Google Earth,
Is this still part of lecture 1?
yes. January, it might label January 27th. So on Google Earth, yeah, that's a good point. I'll make a note when we switch to the second lecture. So here the hand that was at Mount Wellsville, maybe 42 degrees, 24 minutes, 24 seconds. And again, there's 60 seconds in a minute, 60 minutes in a degree. Think of a degree as an hour. And so on the previous slide, let me just, I apologize for the jumping back and forth. But there is a location represented with these degrees, minutes, seconds. So you would read that 42 degrees, 57 minutes, 18 seconds north latitude. 78 degrees, 11 minutes, 22 seconds west longitude. That's not very useful if you want to do math. Obviously, that's not a number. There's quotes in there and degree symbols, and there's an N. You can't do anything with that. So we have, as we talked about on January 27th, we have decimal degrees. So instead of saying 42 degrees, 30 minutes, you would say 42.5. So here is the formula, and every single test one I've ever given has had this on it. So this certainly will be on the test with easier numbers than that. I will ask you to convert one way or the other. So here, there's 60 minutes in a degree. So if the original was 57 minutes, you do 57 divided by 60. So taking a simpler set of numbers, if it's 42 degrees, 30 minutes, you would divide 30 by 60, because 30 is half of the 60 possible degrees, so that would become 42.5. And to make this a number, for latitude, the southern latitude is negative. So 20 degrees south is negative 20. The western hemisphere where we are is negative. So 78 degrees and change west is negative 78. I don't like trick questions, but that's one where it's a semi-trick question that I'll usually ask. Don't forget the negative. And contrary to this, a true decimal degree doesn't even have because of the numeric value, you don't have to put north or you don't have to put west. If you say negative 78.5 longitude, for example, you don't need to put west because it's negative. Because of the negative, you already know that it's west. So that's the closest thing to trick question on the test. Probably I might deduct a point if you put west, and so even if you had the number right. So everyone can understand. So here's the formula. Take the minutes divided by 60, seconds divided by 3,600, because there's 3,600 seconds in a degree. So there's 3,600 seconds in an hour. A test question would almost certainly involve just degrees and minutes, just to make it easier for you to do from a math standpoint. Like I said, I want you to focus on the concept, not the math. But remember that Western Hemisphere is negative for longitude and Southern latitude is negative for latitude. We just kind of reviewed this, but here's an example of a degrees, minute, second location using Google Earth. That's the North Campus, I think. We talked about, again, we're reviewing these projected coordinate systems that we just talked about. This is a projected coordinate system or a planar coordinate system, rectangular. We are now measuring on a flat surface. We'll review projections in just a second. So when you project to a flat surface, you have consistent units. Longitude and latitude aren't consistent. We just talked about that. Now, when you project it on a flat surface, you measure in units like inches or feet, and which is good. An inch is an inch anywhere. A foot is a foot, independent of where you are on Earth. And with a planar coordinate system, you start with an origin of 0, 0. Like math, I've related this to, you did this in math class. It was 7th grade when I did it. It might change now. Where you have a coordinate pair, where the first coordinate is the distance from the origin laterally, and the second pair number is the distance vertically. So that's east-west distance, or x, or left-right. Y is up or down or north-south from the origin. Another term, every coordinate system that's planar has an origin point of 0, 0. Another term you'll see x is referred to as eastings and y is referred to as northing. Questions? Obviously, since it's a review session, please don't hesitate to raise your hand, or never hesitate, but especially now, if you have a question. So a planar or a projected coordinate system is Earth's surface projected. Where I brought in the globe and the flat map, and we looked at that. Remember that? Projected onto a flat surface utilizing a mathematical formula. And then depending on the specific area that you want to map, they choose a different origin. And there's some slides coming up on that. And again, that's done with what's called a map projection. The coordinate system is the measuring system that's used once the map projection is applied. So the map projection is an algorithm or a formula that actually takes the globe and makes it flat. And the coordinate system is the units that you use to measure after that. There are several major categories of map projections. And each one of these graphics shows, it doesn't show the algorithm, but shows kind of in a broad sense how it works. So a cylindrical projection, think of a flashlight. You wrap the Earth in a cylinder, shine a flashlight on it, and then the features of the Earth would move from the globe onto the cylinder piece of paper, which you would unwrap. A very technical way of describing it. I prefer that to some long math formula. A conical projection is not a con, but a cone placed at a strategic place on Earth. Then you shine the flashlight, which would take the features of the Earth and onto the cone, like this. An azimuthal projection is like a serving tray, a flat circle you would place on the Earth at a strategic location and then project the features onto that circle. That's an azimuthal projection. I said the location you choose to put the plane is strategic, depending on the area that you want to map. So if the area you're interested in mapping is Africa, Africa's over there, you would put the plane here. So if you think about that, we'll talk about that in a second. Over here, this is going to be very accurate. The plane is right there. But if you try to use this projection, mapping features over here, you can see the distortion. So that's what I talk about. I talk about this strategic location. As I said, I'll just ask about this. All all just projections are distorted. You cannot represent a curved surface on a flat. The Earth is a curved surface, obviously. You can't represent the curved surface of the Earth on a flat surface without distorting it. And I use the orange peel. To get the orange peel flat on the table, you're going to have to stretch it or push it. And so there are four different ways in which a map can be distorted in a projection. And the acronym is SAD. I credit ESRI, so you didn't think that I came up with this. It's their fault. But I think it makes it easy to remember. SAD is shape, area, distance, and direction. Those are the four things on a map projection that can be wrong. And the algorithm can be designed to make one of these perfect at the expense of the other three. Or some projection algorithms kind of come up with an average where none of them are too horrible, but none of them are completely accurate. So, for example, an equal area projection, and if you haven't done that in the lab yet, you'll see that in a lot of the names. There's a projection commonly used called Albers equal area that uses the map of the United States. On Albers equal area projection, the areas are perfect, but the other three things are off. And here's some names you'll see of projections. Conformal in the name means that shape is preserved. The shape of Utah is correct. It may not be the right size, but the shape is correct. And you can read these here. I won't go through all of them. Azimuthal is an important one for navigation. In the azimuthal projection, the direction is preserved. The length that you measure on the map might not be right. The shape might not be right. I think I showed you a projection where Greenland looks like it's half the planet, where it really isn't that big. Some projections make the polar countries look very big, like Russia and Canada and Greenland. But in an azimuthal projection, even if things look distorted, the direction from one point to another is correct. So especially back before modern navigation, sailors would need an azimuthal projection to set their ship in the right direction. They don't, if they want to sail to the New World, they don't necessarily care that it's 3,000 miles instead of 2,900 miles. That's not as important, as you better be at least going in the right direction. Ask Christopher Columbus about that. He didn't end up where he expected to. And I mentioned often the projection name gives a hint of what it's preserved. And this is a screenshot from ArcMap. The North America equidistant conic projection is one that you might use. So please don't memorize these. It's just showing how these are applied. That projection, we can tell from the name, is equidistant. That means on that map projection, we can measure distances and they'll be correct. The other three things will be wrong. And we can even see that it used that conic algorithm. The cone is the method in which that projection was derived. So sometimes you can tell whether it's cylindrical or conical also based on the name. I don't see one here, but azimuthal projections are the ones where the direction is right. Well, that's on the last slide. So here's some examples of different types of projections and how they look. A couple that preserve area and shape, and the Robinson projection, that probably looks familiar. This is a common projection for world maps. It is a compromise. It tries to get the best of the four, but none of the four attributes are perfect. I think the world map I brought in on roll was Robinson. It's a very common map projection. And I actually used the globe for this, but this map does not preserve direction, so this is what you would perceive on this map as the shortest distance to Netherlands. But if you mapped it, in actuality, that's the shortest distance. And this map also doesn't preserve direction, and you can tell because the shortest distance is in a straight line. And the shortest distance between points a straight line, not on this map. And I should pick, it's more striking if you go to Asia. Like on this map, if we decided we were going to fly to Beijing, you would draw a map like this. But the shortest distance to Beijing is like right over the pole. That's the example I showed with my globe. That's the first lecture. Is there any questions on that? So the key points are the some questions about the projections, not memorizing, but explaining how they can be distorted. Shape, area, distance, direction, things like that. The conversion between decimal degrees and degrees, minutes, seconds, I think are some key takeaways from that first lecture that when we met on January 27th. So I think those are the takeaways there. We'll go into the following week if there's no questions. We continued with the projection discussion. This world Mercator is a common projection. It's cylindrical, so there's heavy distortion at the poles. Think of that. Think of the picture with the globe with the cylinder around it. The poles are the furthest away from the cylinder, so they're the most distorted. So the world Mercator is what makes polar features look huge. For example, here Antarctica looks like it's as big as the whole rest of the landmass, and that's obviously not the case. Greenland looks the size of South America, and that's not the case. So the cylindrical projections really distort the poles. But regardless of that, world Mercator is a commonly used projection. It's been criticized because of this. This distorting, making certain countries seem more important on the map just because of their latitude. Or conversely, Africa looks tiny. Africa is actually a huge continent. It doesn't look very big there, does it? I think I mentioned this a minute ago. USA Albers equal area, and again, I'm just showing examples. I'm not going to say which common projection did I show. But Albers equal area is a common one used for the United States. Doesn't that look? It looks right. I mean, that's a very familiar looking map of the United States. The way it's curved. It's equal area. It's a conical projection, so that means on this projection, the area of Texas relative to the area of Colorado is appropriate. These projections are probably a little more important. I mean, often you're measuring a specific. You're not often making maps of the world. More often you're mapping, water mains in one county, or you're mapping land use in Boston. You're mapping a specific region, and so these projections are more important. There'll be a question probably about one of them. So let's review UTM, Universal Transverse Mercator, and we'll review state plan. So just to review, UTM measures in meters, and it splits the world into 60 vertical zones. I'm more interested in that than the CXIO and all that. More interested that these are the 60 zones. I wish the horizontal lines were off of this. Maybe next year I'll get a better graphic. So this is zone 18. We're in zone 8. We're right between zone 18 and zone 17. So that's UTM, which is a commonly used projection. Each of the 60 zones has its own central meridian. So where we talk about setting an origin point, 0, 0, each of those 60 zones has its own origin point. So that's how that projection is localized for mapping in that area. And I'm not really interested in the specific meridian values of that. And then in the United States, even more localized, we have the state plane zones. Many other countries have their own systems like this for mapping. I'm focusing on what we do in the United States here. So there's 120 specific projections to cover mapping in the United States. And where we are now, there is a projection called Western New York State Plane. And so that projection is defined and set up specifically for mapping in this area. When you use that projection, all four things, shape, area, distance, direction, are very accurate. They may be off slightly, but they're very accurate there. It gets worse as you get away from here. But if I'm mapping, you know, water mains in Erie County, I don't care that my projection is off in Kansas, because I'm not going to use this projection in Kansas. Does that make sense? So state plane zones. Might be worth remembering that there's 120 state plane zones in the United States that are for mapping a local area. I wouldn't ask these specific, almost trivial things, not 2 million feet, things like that. But I mention that because you certainly will, you may have already run into them in lab. You certainly will run into state plane if you continue your GIS career. So what to choose? Do I have pros and cons? Differences between geographic and projected. I could ask you, rectangular systems should be used for any kind of measurement and analysis because you're using consistent units. You shouldn't use geographic coordinates to do analysis, latitude and longitude. Projections make a difference. Look at the differences in the United States, depending on what projection it's mapped with. So I want to get into this. A datum is a known. A datum is a way of approximating the exact surface of the Earth. Geographic coordinate system, the latitude and longitude assumes a perfect sphere, but the Earth is not a perfect sphere. It's an ellipsoid. It's fatter than it is tall because of the force of gravity. And obviously there's other small undulations, like mountain ranges and oceans, which really make less difference than you would think when you think of the size of the Earth. So we use a datum a datum is a mathematical formula that best approximates the true shape of the Earth. And common datums you would see would be the North American datum, 1983, which has been recently updated. That's a datum approximating the Earth, specifically designed for the shape of the Earth over North America. The WGS84 datum is a worldwide datum that, again, is a formula representing the exact shape of the Earth, not a sphere, but the exact way in which the Earth is distorted from a perfect sphere. I might ask the difference between a projection and a datum. So every projection has a datum. So when you project from a sphere to a flat surface, you're not actually starting from a sphere. You're starting from the irregular shape of the Earth. So when I say Western New York State plane project, what is the temperature? What do we usually do? Do you wait it out?
I say we give it like 3 minutes.
Okay. It's up to 8.
Just talk really loud.
Yeah. Of course, the violation of the standard cut is being recorded right now. Out there on YouTube. I'll pause that. Someone's gonna die if they put Tracy right to record this. Are people reading?
Yeah.
The thing is, if it's in like a dorm, they usually come in here during the fire drill because they don't want to go outside.
Oh, really?
Yeah. I mean, as long as it's not setting off like from Fillmore.